I am Walter.
Don't be disguised.
Hey guys.
There.
Okay. Hopefully I fixed everything is good. I got so many emails from last year. No, that's good.
I see your true colors. That's why I love you. So don't be afraid. Show
I'm gonna do the introduction. Someone. Thank you. Okay.
Show me a smile. Don't be unhappy.
Yeah, it is. Yeah, not too close. Oh, that is. I'm surprised they don't have like a mic. Well, they do have a mic stand. You could probably just grab.
Do you want me to go out and just make this happen? Or
Yeah, why don't you get everybody? Yeah,
Yeah.
can we get everybody a? Do you want the mic stand? We could just.
No, it's okay. I'll walk around.
A TV host.
Yes.
All right, I think we're going to begin our next plenary session. It's my pleasure to introduce Professor Robert Pless from the University of Washington in St. Louis to Sibi Grappi. Robert's doing a lot of amazing work these days in very large-scale web camera surveys. What can you do when you have access to thousands of different webcams around the world? This is really, really neat stuff, and so I'm just going to, turn the floor over to Robert and let him tell you all about some of this really amazing webcam work and some forensics work, too, that's coming out recently from his lab. Take it away.
Thank you, Walter. And it's an honor to be here and to give this talk to all of you. So today's talk is about searching for images that we can use to measure the world. And I want to start with a comparison to yesterday's talk, where the argument was that if you have two cameras or depth cameras, that's much more efficient or lets you do more things than you can do with just one camera. So I don't have that viewpoint. I say often you have no cameras at places you want, and just having one image is much, much better than having 0 images. So it's not a contradiction to yesterday, it's just it's an addition. And this is especially relevant in today's world because the world is a big place, but we have more and more and more images of the world. We have it through Twitter and through Facebook and through social media apps like Snapchat and Orkut. We have images that are taken from lots of people in lots of places at lots of times. And sometimes those images tell you something very important about world events. So 2 recent examples are a collection of selfies taken by a Russian soldier that he uploaded to Instagram, which had a geotag, which was awkward because he was inside the Ukrainian territory, even though he was a Russian soldier and he wasn't supposed to be inside, or officially he was not inside the Ukrainian territory. It even showed on other pictures the type of vehicle he was in, and it was a vehicle that launched missiles. So it was a very, very, very interesting selfie feed. Other pictures from social media help show the human effect of different events. So Ferguson, Missouri is 5 miles from where I live, and it was the place where there was an unarmed person shot by police recently, and that led to riots that were there. And some of the pictures posted on Twitter gave a much more real or much more up-close version of what those events were like when there was rioting in the streets than any of the pictures that were from the legal place where the journalists were taking pictures. So my argument today is that for you is that social media imagery offers fascinating challenges for computer vision researchers, especially in terms of taking these images, understanding where exactly they're from, what's in them, and when they were taken, in order to validate and really understand what those pictures tell us about the real world. Sometimes these challenges are expressed in terms of something fun. So there's a blog called The Daily Dish by Andrew Sullivan, and once a week he posts a contest picture. It's called the View from Your Window contest. It's a meme where his readers send him... Wrong button. It's a meme where his readers send pictures of someplace interesting, always taken, so you can see just a little bit of the window in the picture. That's the theme of these pictures. He posts one picture a day to show how beautiful the world is. But on Saturday, he does not tell you where in the world the picture is taken from. So you get a picture like this, and the question is, where in the world is this taken from? There's no information except that it was taken sometime in the last week. And thousands of people every week spend far more of their weekend than their wife or husband would want them to, poring over computer maps and other pictures to try to discover where some place is. And they put together amazing descriptions of how they figured out where it was. So if you zoom in on this bus, you can see it's bus route number 39. Some people recognize that this type of bus is often found in Argentina. And then the final pictures show other pictures that they found from, say, Flickr or online databases that show buildings that look the same and their guess of where that picture was taken from, other buildings from a different viewpoint, other buildings from a different viewpoint. And this collection of other data that's already online helps really define where in the world this picture was taken. There's also, beyond just the context of a game, there are citizen investigative journalists that try to do this more formally. And the best known of these is somebody named Elliot Higgins. And he creates a blog called Bellingcat, where he takes pictures that are posted, for instance, of a video of the death of James Foley, and tries to say where in the world exactly that happened, which can help tell you where various terrorist training camps are. This became most public and was sort of the most useful version of this. Came in this picture, which was taken of the smoke contrail of the missile that shot down the plane Malaysian Airlines MH17. This is a picture somebody took when they saw the missile take off. And there's an amazing blog post that is not on my screen. There's an amazing blog post about this picture that is a very, very long investigative story about how you figure out exactly where in the world this was taken. And some of the highlights of that blog post are finding the trees and the power lines in the blown up version of this picture, and then identifying on Google Maps where those are to provide geometric constraints that say the only place that a camera could be to see those trains, those trees, those power lines at exactly the location in the image is if the camera is here looking in this direction, which means the missile must have been launched along this line. And then I think later pictures showed that one of these fields had tire tracks that are consistent with a large missile launching truck. So one of the things that is fascinating about these stories is how much work it takes professional investigators but amateur geometers, how much work it takes for them to solve these questions. So my mission today is to argue that our community can do really important work in this area by studying a collection of things like making this reasoning easier, more precise, and more quantitative, understanding new constraints that we can use to validate the accuracy of photographs, and perhaps even building new iPhone apps or tools so that when you take images with those tools, it's easier to correlate with other data and validate the changes that you see. So to do this, I'm going to tell 4 stories. One is about Amos, an archive of images from most publicly available webcams. The second is finding a grave that had been lost and building a calibration tool to make that easier for others in the future. Third, formalizing a relationship between shadows, sun position, geolocation, where the picture was taken in the world, and time. And last, a story about repeat photography which is the task of trying to repeat a photograph exactly by standing in exactly the same place and looking in the same direction at some different time, and apps for making that process easier and more consistent. So that's our plan for today. So the first story is a project I've been working on for the last 6 years, and apparently I've bored Walter to tears with it because that's what he hears about every time I talk to him. It's called Amos, the Archive of Many Outdoor Scenes. It's a database we've captured of about 30,000 publicly available webcams. So not a webcam like on your computer, but a webcam that is connected to a web page that is constantly sharing a current live image of some scene. So these are beach cams and highway cams and ski resort cams and traffic cams. There's a lot of them around the world. Every one that we capture is one that creates a web page that anybody could go, right-click on that image, and save as. And so we have a little Java program that does that. And these cameras are located all over the world. Some of them that I like the best are these are 7 buoys, like floats in the water that have cameras on them and weather sensors on them. And we've been logging, saving 1 image every half hour from each of these cameras since 2006. And my goal is to take this collection of images and make it a useful imaging resource, not just for us, but for anybody who'd like to use that. The kinds of things we have to do to support that are to find the cameras to begin with, geolocate where they are, to visualize the data that we have and maybe when we have that data, to calibrate the camera so we can make measurements on that, and then to annotate the scenes so that if you care about a particular thing, like trees, you can find all the webcams with trees instead of searching through them all one at a time. So step 1 is finding cameras. I accomplished this step by hiring 2 undergraduates to spend an entire summer finding webcams. You can sometimes do it more mechanically than others. So if you do a Google search for websites that have view/index.html, that's not very common in web URLs, but it is very common in the web pages that are created by a particular brand of webcam. So if you search for this, you get thousands of pages of webcams that update their images live. Sometimes all you see about those cameras is a picture, and you may not know anything about where in the world that picture is. So the first task is to get the pictures, to understand what pictures you have, and then to geolocate them. So I'm going to talk about those 2 steps, the visualization and then the geolocation. So here's our visualization page. When we think about one camera, we take a current picture of that camera. We can summarize all the pictures that camera has seen for a year in this plot. This plot is organized by time of day and then time of year. And each pixel is the average color of the entire image taken at that time of day and time of year. So we can see days are longer in the summer than they are in the winter. And red indicates a time when we don't have a picture, either because that camera was broken or because our system was broken. So that's a simple visualization. Even that visualization tells a lot of information, but slightly more interesting statistical tricks like principal component analysis can tell us more. So if we run principal component analysis on a set of images, we represent every image as a long column vector of the pixels. PCA decomposes that approximately, that data matrix, into a set of basis images and a set of coefficients. When you have images from a camera that is static, the PCA decomposition is much more informative, even with just a few components, than mostly otherwise. So if we approximate this, we might use only a few basis functions. Those basis functions are overlay images that you can add or subtract from the average image to approximate a particular image. And then coefficients, which say how much of each of these overlay images we need to reconstruct a particular image to begin with. If you have images that are taken over time, those coefficients change in a very regular way over time, often reflecting the major changes that happen in outdoor scenes. So the first coefficient often codes for, is it nighttime or daytime? Nighttime or daytime, nighttime or daytime, because that's a very big effect on outdoor images. And the second effect is time of day. So in the morning, the sun is in the east, and one side of building is lit, buildings are lit. In the evening, the other sides of buildings are lit. And so you can see that we have morning versus evening, morning versus evening, morning versus evening. So if we look at particular images that are coefficients, this is an image taken at night. This is an image taken during a day that has a big difference between the morning and evening, which tends to be sunny days because that's when there's a big difference. And this is an image taken during a day when there wasn't such a clean difference between morning and evening, and that's a cloudy day image. So this highlights that the simplest multidimensional data reduction trick is really powerful for things like outdoor images, but especially when cameras are always looking in the same direction, because we don't have to encode for how the scene changes, we just have to encode for the lighting variations of that scene. So we can now make a summary image that is a little bit richer. We have a picture, we have a summary image that is time of day by time of year, and now instead of encoding the average image, the average color of the image, we can encode here the first, second, and third coefficient for that image in a false color as red, green, and blue of a color channel. So these colors are now false colors, but images that have the same color here tend to look the same as images. So we have the nighttime images are all very similar. And then daytime, sometimes there's days that have this dirty purple color, and sometimes it sort of changes from orange. So that's actually reading off what the weather is every day at this location. So if I go between two different colors, you can see the purple colors tend to be rainy days, and the orange colors are sunny days. And so that's interesting that something as simple as PCA, when you apply it to images from a static camera, gives us weather models for that camera. If you have a camera that does another way of looking at this is you can just look at this color code and say something must have happened here. So in this case, we have the camera moved. And so then the basis that you need to define that camera moved and the coefficients change because the images have changed a lot. One more thing you can do with PCA is to say, let's solve PCA, find the bases that I'm not showing, and the coefficients that you use to reconstruct each image. Then you can subtract each image from its reconstruction and say, how well did these three variations model the variations in this scene? So here's a picture that shows that error. It says it solved all the images were relatively well solved except for one spot. So what happened on that one day? Well, we had an insect come to visit the camera, sits in front of the camera, and changes the appearance. So the first lesson I want to share is that these kinds of visualization tools, while they might not help you get a CVPR paper or a paper in an important vision conference because this is all something that's very well known, if you have large data sets, it's always worth the time to make good visualizations of those data sets just so that you don't have images like this foul up your later analysis, if for no other reason. So that was a little bit about visualizing data. The next step I want to talk about is how would you geolocate a webcam. So this geolocation problem is different than geolocating a single image because I can look at images from a very long time, and I know when I captured those images. So here's a summary of images from 1 year. Now it's time of year by time of day. And you can see that days are longer in the summer than they are in the winter. And you can also see when dawn is at each particular day. So if you know what time of day dawn is, that tells you what the latitude of the, what the longitude of the camera is. The length of the day, how long it's light on a particular day, tells you the longitude or how far north and south. And so this is a cue that lets you geolocate where in the world a camera is. This is most fun for some extreme examples. That's very strange. This picture is cut off. So this is the South Pole. So in the South Pole, it just never becomes dark in the latter half of the year. And so the only place in the world where it never becomes dark is at the South Pole. And so this is a cruise ship. It's a camera that's on the top of a cruise ship that cruises around the world. And so for this camera, as the cruise ship goes between different places, when daytime is, when dawn starts, changes at different times of year. So that's one method to try to geolocate cameras. We can do one step more clever than this. We can take images from a camera. We know that images vary over the course of the day, so to make life easy, we just take pictures at noon. Take a picture at noon every day for a month. If you run PCA on that set of pictures, and look at the first coefficient, you can sort the images by the dominant cause of change. In most outdoor cameras, if you just have pictures at noon, that cause of change is what is the weather. So if you sort the images, you can see sunny to cloudy, sunny to cloudy, sunny to cloudy. And every once in a while, there's a camera where some other factor has a more important influence. So here it's almost certainly weekday and weekend at this parking lot. So during the weekday, you have lots of cars, and the weekend you don't. But most cameras, it's sunny to cloudy, sunny to cloudy, sunny to cloudy. That means that just PCA can give you a signature over the course of a month that this camera experienced cloudy, 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 sunny, sunny, cloudy, sunny, sunny, cloudy, sunny, sunny, cloudy, some kind of signature like that. You can then visit a satellite picture, taking the satellite picture at noon that same set of days, and ask which pixel has the same cloudy, cloudy, sunny, sunny, cloudy, sunny signature. That gives us geolocation estimates. My favorite one is that this is a quarter mile off, so half a kilometer of error for this camera using the satellite estimate. That's actually ridiculous that it's that close, because our satellite map has much worse than 1/4 mile pixel error. So we just happened to be lucky that we were exactly at the right pixel and that the pixel spacing was so close. And we get something like 80% of our cameras within 50 miles of localization error on this approach. Sometimes you want camera geolocation to be much, much, much more accurate. I don't know of an automated way, a fully automated way to make geolocation much more accurate. So I say, let's have people help. And so this is a public website we share. It's called Project Live 3D. The idea is, with people's help, we can geolocate cameras very accurately. And the kind of help we need is to take a picture from a webcam, to identify points in that picture of a webcam, and then identify on Google Earth those same points. So a richer picture of this is a college in Arizona. We find points on the webcam image. We find those same points on the Google Earth image. And then we solve some formulas that I don't need to show you, but they're the standard camera calibration matrix formulas that say, where in the world is this camera? Oh, there it is. So we solve for the relationship between these 3D world points and the 2D image points. And this matrix encodes the rotation, translation, and zoom level, or the calibration of the camera. So when you do that, you can take a webcam picture, and you can solve for an estimate of where the camera is, and then you can paste the texture of that image back down onto the ground plane, which lets you do things now like if somebody is walking across or if somebody is driving here, instead of knowing how many pixels per frame they go, you can measure that in meters per second in the real-world coordinate system. For other pictures, you can take the Google Earth's picture of a mountain and paste on top of it the current conditions of that mountain. And there's also, people love the Eiffel Tower. There's lots of webcams of the Eiffel Tower. Sometimes the Eiffel Tower sparkles at night, and we can capture that sometimes the Eiffel Tower sparkles at night. So this is a set of online tools that we build and share, and anybody can use to geocalibrate a camera. It works best if your camera is in a location that has 3D geometry already in Google Earth. You need to know at least some points that are not on the ground plane. And so if there are points in 3D in the Google Earth geometry, that's an important factor for this to work. But if that's there, then this is nice because it allows anybody to geocalibrate a camera, not just a computer vision expert. And we published this, and it became a little bit well-known, and it got us involved in a story. And I want to warn everybody that this is a little bit of a morbid story. It involves a case of a person that was murdered, a child that was murdered in St. Louis in 1983. And the victim was found not just murdered, but also decapitated. Their head was cut off, the body was found, the head was never found. There was an investigation for about 6 months, and there were no leads, no progress that the police made in this investigation. So they buried the body in a cemetery. And about a year later, some students got together and raised money to put a headstone at the cemetery to honor the crime victim. And this has been St. Louis's most important cold case for 30 years. There's still, 30 years later, no information about what happened or who the crime victim was or who did the murder. So in 2013, they went to exhume the body, to dig up the body in order to get tissue samples to do DNA testing, because DNA testing is now more efficient than it was in 1983, and they thought that would give clues for who the victim was and therefore maybe what the crime was. And one issue was they went to the cemetery and they dug up the grave and they found the wrong body. They found an adult body. And they said, well, this cemetery, it doesn't have such good records. Maybe it's this grave next to it. So they dug up that grave also, and they found the wrong body. And they dug up 4 places and always found an adult body in 4 different times. And the county medical examiner said, you're not allowed to dig anymore until you have proof of where the body is. And probably what happened is a year later when they put this headstone up, they put it in the wrong place even at the very beginning. So we were asked to try to help this, and the approach was to take this picture that was taken the day of the funeral, the day of the burial. This is actually the casket. And here's a picture, and it seems like this is a picture that we could geolocate. And it seems like that would be useful because if we can geolocate where the camera was, the camera is really right on top of the grave. And it seems like there's lots of useful features in the background. Like if we can find these trees, we can find this billboard, that would give enough geometric constraints in order to figure out where the grave was. So that was the approach we followed. We said find key points in the image that might still be present. And those were things like trees we could find, other gravestones, billboards, trees in the background, billboards in the background. So there were several challenges with this. One is that the cemetery was a cemetery that looks like cemeteries often do, sort of a big open field with a few trees. So in 1983, it had that cemetery park-like feel. And from the aerial view, you can see occasional trees. Today, the cemetery has been largely abandoned, and so there's trees everywhere in the cemetery. And the overhead view just shows nothing but trees. So it's not anymore a nice park like this, but there's trees everywhere. And one thing that's interesting about this from the computer vision standpoint is we often think about computer vision from the perspective of it's a very young field. There's not that many people that think about images that are 30 years ago or think about what images might look like 30 years from now, but the world is a really interesting place, and lots of things change over the course of time. The second thing is if we want to use these points that we can find, we need to know what their coordinates are. And so we went out first with iPhones, and we said, okay, here's a point, and here's a point. The iPhone gives us GPS coordinates. These iPhones are not very accurate. It's only about 2 meters accuracy, even if you just sit there forever. So eventually we got really, really good GPS. This is a differential GPS that gives to within something like 3 centimeters. It's amazing that this device works, 3 centimeters. So we found these points on the images, and then we found the coordinates of those points in 3D. Some of the other challenges are some things that were there that would be really useful corresponding points aren't there today. And sometimes they're even not there today in tricky ways. So this is a billboard. There is a billboard very close to there right now. When we tried to use those corresponding points, it just never worked out. So this billboard was cut down, and a new billboard was built about right here. And so it looked like a good corresponding point, but once we realized this point never worked, we went back and we found like 1 foot high off the ground the old legs of this billboard where it was cut down, so we could fix that. Some of these trees have been cut down since then. This billboard no longer exists at all. So we built a tool that I'm going to demonstrate a little bit later, and our tool said, let's find points in the world and represent those as these circles. And then let's imagine if we had a camera and we know where the camera is and what direction the camera is looking, and that camera is looking at 3D points in the world, where on the image would they appear? And so ideally all the squares are exactly on top of the circles. And we built this tool to try to estimate what our error was. And so because there's several sources of error, like the GPS coordinate might not be quite right, or the camera might have some error, we solved 1,000 different times, continually adjusting our GPS estimates to give a sense of the effect of GPS error. That gave us a 95% confidence interval that the camera was at this location plus or minus about 1 meter in either direction. And the end of the story is that my student Abby went out the day they were digging this up, and we were within 8 inches of where they dug. And it was actually a very crazy story. They dug about 2.5 feet, and they found an adult body. And they said, okay, maybe we should go to the next place because you have this uncertainty. And my student Abby, because she's a first-year PhD student and doesn't understand science yet, she said, "I'm very sure we're right. You should keep digging in this first place." Like, I would have had 50 perfectly valid reasons why we were wrong, but she hasn't been trained yet. So she said, "Keep digging." And they kept digging, and that's where they found the body. And part of the reason she was confident to say that is she found that this cemetery actually went out of business 20 years ago because they were sued for double selling grave sites. So they were actually, it's not so unlikely that they have two graves on top of each other. But they managed to find her. They did the tissue analysis, and it was just 2 or 3 weeks ago that they found that they do not have any DNA match, but using isotope trace analysis from the bones, they know that the victim is from very close to the Gulf Coast of the United States, so Florida to Texas, somewhere within 10 miles of the ocean, because that's where that particular type of isotopes come that get embedded into the bones. So maybe that's a clue that will help them go to a next step. We don't know. So in order to support this, we built this tool called geocalibration.org. This is sort of similar to Project Live 3D, but it's entirely a 2D calibration project. This is also a live website. It has better usability than the other one. So if you only need to know where a camera is and not where it is in 3D, I recommend you use this. I just want to share how it would work if you actually want to go use it right now. You go to geocalibration.org. It gives you this picture. You put in the URL of the image, so some web address that gives you the image. Then you need to navigate yourself to about where in the world this picture is. This website is not magic. It requires that you find corresponding points between the image and Google Maps. So you have to get to close to where it is. And then it gives you an interface where you can take 4 points and put them on locations on the image that you might be able to find on Google Maps. So you take these colored points, you put them on the image, then you find exactly the same points in Google Earth. So the 2 corners of the courthouse building are these 2 corners. This is the corner of this red building. This blue point is right in the middle of this fountain, and if you zoom in on Google Maps, it's easier to see this. And then it solves for the location and the view angle and direction of the camera. If you're doing a class in camera calibration, if you click on this button here, it shows you all the dirty details of the exact camera position and heading and focal length, so you could reconstruct the camera projection matrix. And it shows you the image locations and the GPS coordinates of all the corresponding points you had. And that lets us play games like we can now change what we think the camera focal length is. So if your camera is a camera that you know and you can calibrate, you can set the focal length to a known focal length of that calibration, and it'll update what the camera view frustum is. So if you watch, this focal length slider is changing, whoops, and it changes where the camera is. And in each case, what it's doing is, if you set a focal length to be something particular, it's resolving for where in the world the camera could be to best have all these points, match all these points, given the constraint that the camera focal length has a particular value. Geocalibration. All right. So now the next story I want to tell is beyond just collecting images and trying to build tools that we make publicly available to find where in the world they are. What are things we can do if we know exactly where in the world the camera is? What are new constraints we can provide? So one thing that I have long thought and been inspired by is shadows. Shadows give you incredible constraints on what the 3D geometry is of a scene. We can look at this picture and understand a lot about what the strict structure is here by seeing these shadows. And so we wanted to phrase the problem, suppose I have time-stamped images from a camera that I know where in the world it is and what direction it's looking. If I have all that, I can look up what the sun position is for each camera, where the sun must have been, because that camera was at a particular place in the world, and that place in the world, the sun must have been at a particular direction, so we know what direction the sun is. If we know that sun position and we can find correspondences between a point in the scene and the shadow that it casts, can we use that as a cue for 3D structure? So here is that constraint. So suppose I have this point. This is an interesting point because it comes from this building, and this building has a stair-step structure, and you can see that stair-step structure over here on the other scene. So if we solve for that So we can ask the question, where could this point cast a shadow? So we might be able to look at this and say that's probably the shadow point, but that's a hard computational problem to get started with. So we can say, what does knowing the location of the camera help with that? So here's our point. Classic 3D geometry for computer vision. All the learning, machine learning stuff. I hate that machine learning stuff. I just like geometry. So I have a camera. If I look at a point, that point must come along some ray in the camera that's along direction r and depth d. So somewhere along this ray is a point. If I know where this camera is, I know the sunlight has some particular direction. I can solve for the equation of that. That means that the place where this point casts a shadow has to be somewhere along this line in 3D. We can project that back to the image and say that has to be somewhere along this line in 2D. So there's a constraint of where shadows must lie. Because this is similar to the epipolar constraint that people use in stereo geometry, we call this the episolar constraint, because it's a constraint based on the sun. So that says that the shadow must lie along this line. And so in this case, that shadow point is right here. So what does that tell us about 3D structure? That gives us a constraint between the depth of the red point and the depth of the blue point, because we know these 2 points in 3D have to be separated by a line that is exactly parallel to the sun direction line. So we can write that out as an equation that says this 3D point that's along this ray with its depth, plus the lighting direction by some unknown distance, has to match the depth, has to hit this ray, and has to hit this ray at a point at a particular depth. So that gives us a constraint between the unknown depth of one pixel and the unknown depth of another pixel. So that's a constraint that we can have if we can find correspondences between these points. So how could we find correspondences between these points? So one approach is to say, let's pick a particular starting pixel, follow our episolar line, and say it has to go, the corresponding point has to be along this line. So it's a very naive rule. Let's only consider pixels that are at the boundary of sun and shadow. And let's just imagine that they go into the shadow, and the first time they hit the sun is the corresponding point. That's a very naive rule. It just says I'm going to start at a location and go until the first point. I'm going to start a location, go until the first point. These might be valid correspondences. That corresponds to here to there and here to there. This is an invalid correspondence because the place where it starts is actually itself a shadow boundary. So this very simple rule gives us many valid correspondences and some invalid correspondences. But we have images from many times of day. So some of these we can throw out, some of these bad correspondences we can throw out with really simple rules. So rule number 1 is if you're a part of the scene that casts a shadow, you cast many shadows. So this roof, this casts a shadow, half an hour later it casts a shadow, an hour later it casts a shadow, 2 hours later it casts a shadow. This point is we only believe it's casting a shadow at the one time where the shadow actually is here. So places that cast many shadows, we believe. Places that themselves are shadows, and therefore they don't cast the shadow, we don't think they cast the shadow very often, we can throw out. Rule number 2 is shadows move. So if I have a point here and it casts a shadow, it looks like this point might cast a shadow there by our naive rule, but lots of shadow points end here because this isn't really the end of a shadow, it's really the edge of a building. So if we throw out correspondences that end at the place that often are the ends of shadows, then we can throw out all of these correspondences. So we just keep the green ones. So these 2 rules serve to give us a really nice set of correspondences, and we collect these correspondences not just from one image, but from many, many, many images. So this gives us a set of many examples of these constraints. From this image, when the sun is some different place, we get constraints along different lines, maybe between different pixels. This lets us create one very big linear equation that's mostly sparse. It has 2 non-zero elements per row and have an unknown vector of all the depths of all the pixels in the scene. And you might say, if this is so sparse, how could we possibly make one depth model for the whole scene? But it turns out that we get a big linked network of constraints. So from this frame, we get a lot of constraints, but one of them gives a relationship between this point and this point. A frame later gives us a relationship between this point and this point. Another frame gives us a relationship between this point and this point. Another frame, another frame, another frame. And so we get constraints between all the pixels in the scene because at different times of day we get different directions of the shadows. And so here's some qualitative results. Here's a picture of the Half Dome in Yosemite National Park, and here's a depth map of that scene created exclusively from these shadow correspondences. Here's a house at the base of a telescope in Hawaii, and some example correspondences, and the 3D model that we get from the scene. Here's a fake data scene that we made just to evaluate the algorithm. And here's the original depth map and the recovered depth map. And the only mistake we make is in this area, which is actually a place where there was never a correlation. There was never this was its own component. We never found a link of these pixels to some pixel to some pixel, connected it all the way to the original. And this method of solving for depth still has a scale ambiguity, like a lot of computer vision algorithms have. So if the world was half the size and the camera was half as far away, all the images would look the same. So this has a different depth scaling because it never got connected to the big network. So this is an example of things you can do by understanding where a camera is in the world and understanding relationships between the structure of the scene, where the camera is, what the direction of the light is. To get the direction of the light, you need to know where the camera is and what time the picture was taken. So this takes us back to our social media picture. So this is a picture that became famous on social media. It also relates to the shooting down of Malaysian Airlines Flight 17. This is a picture of the kind of truck that the Russian army uses to carry the missiles that get high enough to shoot down a commercial airliner at 30,000 feet. So there was a project to track all the sightings of this truck. And this is taken about half an hour after the shooting in a town that's very close to where the earlier social media analysis said we think where the truck is. And this picture was posted to Twitter, and almost immediately Russian propagandists said, how do you know that that picture was taken at the time that the Twitter post said it was taken? How do you know it wasn't taken 4 weeks ago? So that's the kind of question you might have about this picture. So we used our tool to try to figure out exactly to geocalibrate where this camera was. So we found corresponding points in the image, corresponding points in the world, and solved for the location of this camera. Because we have the location and the estimated time from Twitter of that camera, because we have the location, we then found corresponding points. It wasn't that easy to find corresponding shadow points, but the top of this ledge gives a correspondence down to the ground. And one of these balconies has a correspondence to the wall in the scene. So we have these two shadow correspondences. The Twitter post, in the metadata of the Twitter post, there is a Unix timestamp that you can convert to time, like day and time. And using that day and timestamp, we can say what is the episolar line for that location on the Earth, that camera calibration, then timestamp. And so that gives the red line. And so the red line matches so closely to the yellow line that it's unlikely that this picture was taken at a different time than the Twitter post. And so that counteracts the questions that some people were putting on the validity of this picture. It doesn't say that it couldn't be an artificial picture. It just said that it's harder to make that artificial picture. So that's our efforts on trying to validate pictures that we get and create new types of constraints based on understanding natural processes like shadows. The last story I want to tell is a little bit more fun of a story, and it's a story that I'm asking more enthusiastically for everybody to get involved in. This is a project we call Rephoto. It stands for repeat photography. So repeat photography is the process of trying to take the same picture again. We made an app. It's free for the iPhone and Android that helps make it easier to take a picture and then come back and take a perfectly aligned picture sometime in the future. And so the app has a couple stages. First, there's a database of active projects where people are hoping that there will be more pictures taken over time. You click on a pin in this app, and it shows you the previous picture so that you know you're looking at the right tree or the right building or the right stream or the right bridge. It shows you the previous picture half see-through. So as you're trying to take the picture, you see the previous picture half see-through, so you can align it to be exactly the same. And then you upload the picture to a database, and then there's visualization tools to try to understand how that scene has changed. Now, one thing that's amusing we found is we built this tool to try to make it easy for people to take exactly aligned pictures. It's a little bit hard to take exactly aligned pictures. But we realized we were getting pictures that weren't taken from exactly the same place. So we ran those pictures through a program called Bundler, which explicitly requires pictures to be taken from slightly different viewpoints to build 3D models. And so here's a 3D model of the tree that we built. And I've never seen any other tool that gets untrained volunteers to take pictures that are as good for Bundler, because usually the problem with Bundler is you take pictures that are too far apart, and the SIFT feature matching never actually works. So if you give people a tool to take exactly aligned pictures, you tell them to take exactly aligned pictures, you give people a tool that makes that easier, then they finally take pictures from close enough that the Bundler 3D model happens to work. One of the things that's nice is we built and publicize this and make it freely available and support the backend, like save the pictures for anybody, any project that anybody wants to do. So we have projects that are as far away as Tasmania in Australia, in Zurich, in Scotland, and people just capturing how a particular botanical garden changes over time, or capturing how this tree flowers, or capturing the health of street trees in urban environments. In particular, in this project, they're interested in understanding, are there dogs that are peeing at the bottom of the tree, or is there garbage at the bottom of the tree, because that turns out to have a huge impact on the health of those trees. And so this gives them a tool to recruit volunteers in order to document the local environment of these trees. So the street tree growth project is one of our biggest ones. And sometimes we get really pretty pictures. And then another reason to try to just share tools, and especially share them and not make people like send you an email to sign up, is you get people that are just do things. They go and they try, and they can download everything and just do it. And the barrier of just sending an email makes it so much less likely that somebody's actually going to adopt the technology. So this is somebody that adopted our technology in a completely unexpected way. And it's somebody I'm jealous of, because he arranged to live 9 months out of the year on the Galapagos Islands and 3 months of the year in St. Louis, and all he does is take pictures of turtles. And he gets volunteer groups to take pictures of turtles to understand how many there are and where they are. And so he asked if he could use RePhoto, and we said sure. And turtles don't all look the same, and they're not all in the same place, so it's not a classic repeat photography task. So he uploaded a little line drawing of a turtle. And the point of this line drawing is now when people take pictures of the turtle, they take pictures where there's enough pixels on the turtle itself to actually see something about the turtle, and there's enough pixels off the turtle so you can see if the turtle is on leaf or on grass or on sand, or what kind of environment there is on the turtle. And then once we had all this turtle data uploaded by them to our servers, we decided to try to run SIFT and Ransack on it. And so it turns out we can actually get individual turtle signatures, because the turtle shells are unique. So you only get the SIFT Ransack pipeline matching if it's the same turtle. And this picture is a little hard to see, but I claim that this is the same turtle, but there's this antenna on the back. There's an antenna here. So this is a GPS tracking antenna, and it's different. So we thought this was a bad match for the turtle, but it's actually, they caught this turtle and replaced the battery, like updated the GPS tag. So it's a different GPS tag, but it really is the same turtle. They checked for us by looking at what the GPS tag numbers are. And so the hope is in the future that the turtles we can track just by these photographic techniques, rather than having this big handle for a bird to take the turtle for dinner with. So there's a website for this called projectrefoto.com. If you download the free app, you can contribute to projects, or you can make a new project of your own. So if there's some place that you want to just watch, like how does that tree grow over here, you can make a new project, and either yourself or other people can take pictures. You can take RePhotos also just on your own phone and not share them. So this is my deep fat frying turkey for Thanksgiving in the United States, before and after I took it out. And me and a friend of mine, our eyes, so you can RePhoto anything you want. It doesn't have to be ecological projects. So I want to end with sort of 3 messages. So messages to students is that a lot of times the things that I've found that become best known are not the technical components that are in your papers, but often only the technical components in your papers are what you share, because that's what you get to publish. But building websites that share data or analyze data, even if it's something that's already been done, like that's often a really good way to get unexpected benefits of the work you do. Message to faculty is spend time to learn about Twitter, Vine, Snapchat, and other social media, because this is where so many more images are coming from than standard locations. There's something like 300 million images a day on Snapchat. There's 400 images a day uploaded to Facebook. It's going to be the things that we're going to have to analyze in the near future. And if there's anybody in charge of funding things today, fund efforts to create, support, and share data over a long term, instead of just the cool new research things. Like, it's much harder to get funding for these things, even though they have a bigger impact than it is for new research ideas, and that's a shame. So I'd like to end today just by thanking the students that have worked on this with their love, and some of the people that have given money for this. And I would be very excited to take questions.
Right, that was a great talk. We have a lot of time for questions, so please don't hesitate.
Hi, thank you for the thought. I was wondering on shadow correspondence, if it's also possible to do it when you have different camera position, because other pictures you showed are from the same position and then a different time of the day, different shadows. But if you have different camera positions and you find the correspondence between the cameras, could you also track the shadow correspondence over these images?
So, okay, so that's a great question. The answer is I'm not sure. So if you have a single camera viewpoint, then the question that you're answering is easier, because what you're solving for is a depth at each pixel. If you have different camera viewpoints, then you need a different representation of the depth of that scene. And if you have different camera viewpoints, it probably matters. It would be important to know if you have the pictures at the same time from the different viewpoints, or at different times from the different viewpoints. The constraint still holds. If you have this pixel and this pixel, like the 3D points corresponding to those pixels have to lie on that episolar line. It just becomes more difficult to tie them together between multiple cameras. Yeah. It's a good question.
Hello, thank you for the great talk. I am very curious because the solution that you mentioned about using PCA to detect events, it's so simple and so cool. I was wondering if this type of solution was inspired, or on the other way, could inspire the detection of events from images from the space, because it seems that nowadays we have a lot of images from the space that also could be infrared or other type of images, and it seems that's a good solution also to detect events with stars or explosions or something like that, or even, for instance, events on thermal plants, for instance, if we keep monitoring thermal images, for instance.
So I agree. I think the biggest factor that makes the PCA approach work is having images from consistently static cameras. Because as soon as the camera is moving, the PCA components have to encode for that motion. And so the reason that in our first couple components we get interesting features of the scene is because our images are static. So satellite images can often be very well registered, but you'd have to make sure to register them first. I think if you have to resample them because the pixels don't exactly line up, that's probably okay. But they would have to be very well registered. Otherwise, I don't think there's any substantial difference between thermal images and these kinds of images, as long in terms of this, as long as they are they're well registered. Yeah.
Other questions? Well, I have one. So with this image here, you mentioned, right, that it's probably correct, right, with respect to your analysis. Is there some way to bound the probability of it being, correct? I mean, I guess it's a function of, is this a forgery, yes or no? The error rate of your algorithm, right?
Right. So for this picture, we did not do the analysis of is this a forged picture. We just said, are the shadows consistent with the time that it was reported? And that's a direct answer to the question about whether this picture was taken when the people on Twitter said it was taken. And so it's really interesting, the social media conversation that happens around events and the pictures. There's really strong vested interests in things being true or not true. And so people say, well, how do you know that this wasn't taken 3 weeks ago? And the answer is it could have been taken 3 weeks ago, but it was really lucky that 3 weeks ago we took a picture at exactly the time of day that is consistent in terms of its shadows with the current hypothesis about when this picture was taken. And people don't usually think about probability densities when you have antagonistic antagonistic systems. So I don't know how to answer that in terms of a probability. We can just say that and maybe you could, the chance that we happened to that 3 weeks ago or some previous time when it wasn't suspicious for this truck to be there, happened to be the right time of day. We could measure, I think it was something like a 15-minute window when we would have this small of an error. And so maybe you can say 15 minutes divided by 24 hours is your probability or something. But I think that's a really important question, validating these types of results. I don't know what the right metrics are for that validation process. These shadows were manually tagged, yeah. So we clicked on this point and clicked on a point down here.
I really enjoyed your talk. Thank you very much. What is the next stage? I mean, I'm sure you're full of ideas. At least that's my impression. Is it the state of the foliage of the vegetation that changes over the year? And there are sure other factors in images that can be used to calibrate them, registrate them in time, in space.
Yeah, so I have several active projects and we're pursuing many things. One thing I'm most interested in is understanding from the webcams, understanding the foliage of trees and how that changes over the year and how we can correct satellite estimates of when trees become green in their growing season. Another thing is I try to take the messages that I give to others to heart myself. And often in these pictures where we're trying to geolocate a picture that's on Twitter, it's very often the case that there's many pictures on Twitter of the event, but none of them by themselves are able to be geolocated because each picture doesn't have that many things in the background. And so we're going to extend the geocalibration tool so you can first do stereo analysis for the several pictures that were all taken at the same time, get that as a cluster of cameras, and then if there's one faraway hill you can see in one camera and one lighthouse you can see in another camera, even though you can't geolocate any one camera by itself, maybe you can geolocate the whole cluster. So that's the sort of web development tool project that we're going to work on next.
So something funny happened in a session this year at SIGGRAPH, that there was this paper that is more related to your work than another paper that came right after it. So one paper was they're trying to detect forgeries of images. So basically, just by looking at the shadows and you can bound the position of a light source, then they can see whether this is a valid position of a light source that would satisfy that. Now, the paper that came right after it was how to fake an image so that it is consistent with the positions of the light sources or something like that. So I was wondering, have you considered a possibility that some adversary is going to use your tools to help Russia fake images saying that they were not in Ukraine or something like that?
I guess that's something to worry about. I haven't worried about that. I think in general, understanding truth about images or truth about a particular image is always a good thing. and making tools so that it's harder to make forgeries, even if that tool can then be used to say, well, if this is how you're testing, then we can fix. But it makes the amount of effort it takes to make a good forgery go dramatically up. And especially in the world of Twitter, it's an interesting world because you're not just like one image versus another. There's always more images on Twitter than you know about, and so it's really hard to say forge something to counteract one image, because then there's going to be 20 more that come back and prove that you were wrong, and maybe that affects people sometimes too.
Any more questions? All right, let's thank Robert then one more time. We have one announcement before we leave, so I'm going to turn over the mic here.
Thank you. I just wanted to say that we still have some tickets available for dinner tomorrow. So either for people who have registered but not paid for the dinner, and also for people who want to bring someone along. So if you want to buy those, you can look for me at the break. Thank you. Yes, we have a fast forward session beginning in 15 minutes, right? Yeah. Fast forward session regarding the 2 workshops that we have tomorrow. And people are going to be ready in a moment. So all the people who have works to present tomorrow should come to the front to organize the session, please.
Oito apresentações.